In this video, I will illustrate with an example how to use the derivatives of a function to study its monotonicity and its concavity. Here is the exercise. I am looking at the function f defined by f of x equals x to the 6 times x plus 3 cubed. I want to find the intervals where it is increasing or decreasing, the local extrema, the intervals where it is concave up or concave down, and the inflection points. And with that information, I want to sketch its graph. Before doing anything else, let's remember the tools at our disposal. First, on an open interval, if the first derivative is positive, then the function is increasing. If the first derivative is negative, then the function is decreasing. If the second derivative is positive, then the function is concave up. And if the second derivative is negative, then the function is concave down. That's on an open interval. On a closed interval, however, we require the same conditions only in the interior, and at the endpoints we just need continuity. For example, if the first derivative is positive on the interior of a closed interval, and the function is continuous at the endpoints, we can conclude that the function is increasing on the whole closed interval. It does not matter what the derivative is at the endpoints. And finally, some points are candidates to be special points. At the local extremum, the first derivative must be 0 or not exist. At an inflection point, the second derivative must be 0 or not exist. Notice that it does not go the other way around. For example, if the first derivative is 0 or does not exist, I cannot conclude we have a local extremum. That is why I call these points candidate points. Okay, back to our problem. To make things easier, I have already computed the first two derivatives and factored it. Factoring helps determine when they are positive, negative, or 0. At this moment, I invite you to pause the video and try to solve the problem. Then, continue watching. I need to find out when these products are positive or negative. There are many ways to do this. Here is one. I have drawn a real line here, and on it I will put the values of x where any of them is 0. There is at x equals 0, minus 3, minus 2, and also minus 3 halves and minus 5 halves. First, I will examine the first derivative. The first derivative is 0 when x equals 0, when x equals minus 3, and when x equals minus 2. And on its interval between any of these 2 points, the first derivative doesn't vanish and is continuous, so it's either always positive or always negative. For large values of x to the right of everything, this is going to be positive. At 0, the term that vanishes is x to the 5, and x to the 5 changes sign from positive to negative, so the product will also change sign from the right to the left of 0. At minus 2, the term that vanishes is x plus 2. X plus 2 changes sign from the right to the left of minus 2, so the product will also change sign. But at minus 3, the term that vanishes is x plus 3 squared. Because of the 2 in the exponent, x plus 3 squared doesn't change sign from the right to the left, so the product does not change sign either. Now that I know the sign of the first derivative, I can figure out the intervals of monotonicity. The first derivative is positive to minus 3, so the function is increasing. And I can include minus 3 because the function is continuous at the endpoint. So the function is increasing all the way to minus 3. And for the same reason, the function is also increasing from minus 3 to minus 2. I can put those two things together and say the function is increasing on the interval from minus infinity to minus 2, including minus 2. Now the derivative is negative from minus 2 to 0, and the function is continuous at the endpoints, so the function is decreasing from minus 2 to 0, including the endpoints. And then the function will be increasing after 0. And there is more. At minus 2, the function changes from increasing to decreasing, so we have a local maximum. And at 0, the function changes from decreasing to increasing, so we have a local minimum. For the purpose of graphing, it's going to be convenient to have the y-coordinate at those 2 points. I can obtain that using the equation for f. Let's move on to the second derivative. First, the second derivative is 0 at 0, -3, -3/2, and -5/2. And I'll proceed like before. For very large values of x, this expression is positive. At 0, the term that vanishes is x to the 4th. X to the 4th, because of the 4 in the exponent, doesn't change sign from the right to the left of 0. So the product won't change sign either. At -3/2, the term that vanishes is 2x plus 3, which changes sign. At -5/2, the term that vanishes is 2x plus 5, which also changes sign. And finally, at -3, the term that vanishes is x plus 3, which also changes sign. Now that we know the sign of the second derivative, I can figure out where the function is concave up or concave down. The second derivative is negative all the way to -3. The function is continuous at -3. So the function is concave down from -infinity to -3. And I can do the same argument on the other intervals. The function is concave up from -3 to -5/2. The function is concave down from -5/2 to -3/2, and concave up again from -3/2 to infinity. Now, at every point where the function changes concavity, we will have an inflection point. So I have 3 inflection points at x equals -3, -5/2, and -3/2. Like before, to sketch the graph, I will probably want the y value of those points. I can obtain it by evaluating the equation for f. And for these 2 points, I put an approximate value because for the purpose of graphing, that will be more useful than a complicated fraction. Now let's put together the behavior of the first and second derivative to figure out the shape of the graph on each piece. Between -infinity and -3, the function is increasing and concave down. From -3 to -5/2, the function is increasing and concave up. From -5/2 to -2 is increasing and concave down. Then decreasing and concave down. Then decreasing and concave up. And increasing and concave up. Finally, let's look at the shape around each of the special points. At -3, the derivative is 0, the concavity changes, so I have an inflection point with a horizontal tangent line, and the function remains increasing on both sides. At -5/2, I also have an inflection point where the function remains increasing with positive slope. At -2, I'm going to have a local maximum. At -3/2, I have an inflection point where the function remains decreasing with negative slope. And finally, at 0, I have a local minimum. That should be enough to sketch the graph. Let's do it. First, I draw some axes, choosing an appropriate scale for the important points I found. Then I will include all the special points. And finally, I draw the graph, paying attention to the shape on each interval and to the shape near each special point.